Hello? Hello. Okay. We have got all the technological pieces working, I believe, so we're ready to get started. Welcome to the first two seminars of the 2022 Chemistry Senior Experience Seminar Series, which is in person and also on Zoom. Wow, lots of things going on. So we're going to be hearing from our first two speakers, Ezra Marker and Gloriela Gonzalez today, and Stefan Debert is going to be introducing our first speaker.
Hi, it is my distinct honor and pleasure to introduce Ezra Marker. Ezra is, was, I guess, before they graduated, right? One of my research students, and even though we worked, and actually you'll see another one of my research students, Gloriela Gonzalez, later on. M. Harper is here, so lots of folks in here have done work. And that was a hard time, right? So during the pandemic, what does a research community look like? I certainly had that question. And so it was really great to see students unbowed by that challenge and really take on some really difficult stuff. And so I was really excited. This past winter, Ezra and I wrote a book chapter together that we'll see some of the stuff here maybe there, but it really gave us a chance to dig into this material and take a really broad view. And I really appreciated somebody sort of helping me write and holding me accountable, and it was a really cool thing. So if you want to do that, just Google Marker Debert, and the link will take you to the book chapter. Do I need to keep stalling?
Maybe.
Yeah, cool. So, born in the Twin Cities. What? Born and also somewhat. Oh.
Yeah, I was born in South Korea.
Born in a junkyard. Raised in a. Yeah, no. So, as a reminder, this is a new room. These are our first talks that we are having in this beautiful Science Commons. And please do, if you have people off campus, or actually your non-science students, bring them in here to show them how cool it is, because this is a really important thing. Now, all right. Ezra will be continuing their education at Northwestern University in the fall. We are very excited to see the kind of cool stuff that they'll be getting up to there. So without further stalling, I'll send it over.
I don't know if, okay. Hi, as Stefan and Rachel said, I'm Ezra Marker. My pronouns are they, them. And for the past year and a half, I've had the pleasure of working with Stefan on synthesizing antiparasitic heterocyclic compounds. Now there might be people in the audience wondering, what does that mean? No worries, we're gonna go through it. So before we deep dive into my presentation, I just want to give you a little overview of what I'm going to be talking about. So we're first going to go over what is schistosomiasis, because that is what my research is centered on. Then we're going to go over what current treatment is available and how my research is relevant to the available treatment. And then we're going to go over what past research has been conducted or what Stefan has done. And then we'll talk about what I have done and then what future work can be done. So what is schistosomiasis? So schistosomiasis is a neglected tropical disease that affects millions of people. It's caused by blood flukes of the genus Schistosoma. And so when someone is first infected with schistosomiasis, they're asymptomatic at first with delayed symptoms. So what that means is within 1 to 2 months of infections, symptoms may develop, including fever, chills, cough, and muscle aches. And without treatment, schistosomiasis can persist for years. Signs and symptoms of chronic schistosomiasis include abdominal pain, enlarged liver, blood in the stool or blood in the urine, and problems passing urine. And chronic schistosomiasis is also linked with diseases in the kidneys, spleen, liver, bladder, and intestine. So essentially, schistosomiasis is a parasitic disease that wreaks havoc on the digestive system of humans. So where is schistosomiasis prevalent? So you probably haven't heard of schistosomiasis unless you've talked to me in the past year and a half about my research, because as we can see from this map, schistosomiasis is not super prevalent in the United States, right, in North America. So schistosomiasis is prevalent in Africa, where S. mansoni and S. hematobium are present. South America, where S. mansoni is also present. Southeast Asia, where S. japonicum is present, and the Middle East. And so my presentation and my research is going to be focused on S. mansoni. So what is the life cycle of S. mansoni? So we can think of this life cycle as occurring in two halves. So the first half begins in fresh bodies of water. And the life cycle starts with eggs that mature into Miracidia, which is the parasite that infects snails, which live in fresh bodies of water where people do daily activities like bathing, cooking, and cleaning. And so once inside the snail, the Miracidia will mature into Sacchariae, which is a microscopic form of the parasite that is infectious to humans. And so the Sacchariae can then penetrate the skin of humans, which isn't a painful process, but just essentially how they get into our bodies. And so once inside the body, the Sacchariae will migrate to blood vessels surrounding the liver, and there they will mature into adults and wreak havoc on humans. And then the adult parasites can then produce more eggs, which are excreted back into fresh bodies of water. So two interesting things is, one, when the adult worms are inside of human bodies, the male worm will kind of curl around the female worm, almost in like a spooning position, which when it happens, we do call it spooning because they are essentially spooning, which I think is really funny. And then the second thing is symptoms of schistosomiasis occur not because of the worms, but because of the body's reaction to the eggs that they lay. And so eggs shed by the adult worms that don't pass out of the body can then become lodged in the intestine or bladder, causing inflammation or scarring. So the current main treatment for schistosomiasis that is on the market is a drug called praziquantel or PZQ. In 1972, these two scientists named Merck and Bayer tested praziquantel among 400 other drugs in efforts to develop a commercialized treatment against schistosomiasis. In the 1980s, praziquantel was used as a treatment against schistosomiasis in humans. Prior to that, it was a veterinary treatment. And it has a half-life of 1.5 hours. Praziquantel is super advantageous for a variety of reasons, including it is safe and highly effective against all adult worms of schistosoma. So what that means is that we don't have to determine what species of schistosoma has infected a human to treat them against schistosomiasis. We can just give them praziquantel, which makes our lives much easier. It is also rapidly and completely absorbed in humans via oral administration, which means we don't have to deal with like needles and injecting someone and then having a safe and clean way to dispose of those needles. And it is also used to cure other diseases. So essentially, it's a safe, highly effective, really useful drug to have, right? However, there are disadvantages. So for instance, it's ineffective against juvenile worms, which means that people infected with schistosomiasis essentially have to wait until all of the worms inside of their body have matured into adults so praziquantel can be effective against them. It also cannot prevent reinfection, which means even if you got infected with schistosomiasis, then took praziquantel and hopefully got rid of all of the adult worms in your body, you could become infected with schistosomiasis again. Side effects of taking praziquantel include nausea, vomiting, abdominal discomfort, anorexia, and diarrhea. Now, the biggest disadvantage of praziquantel, and basically the basis of Stefan and I's research, is that there's a risk of resistance, right? It was discovered in 1972. It is now 2022, which means we've been using it for 50 years, right? So there's no naturally induced resistance that we have seen, but resistance has been induced in labs. So it's not a question of if schistosomes will become resistant to praziquantel, it's a question of when. And so with that, I'd also like to talk about OXA, which is another secondary treatment for schistosomiasis. So development of this drug as an anti-schistosomus drug began with a study of a Pfizer compound UK3883. And the hydroxymethyl metabolite of OXA showed excellent anti-schistosomus activity in both mice and humans, which confirmed that it was an effective treatment against schistosomiasis, right? It also has a half-life of 1.5 to 2 hours and is mostly excreted through the urine. However, one reason that I brought the drug up is because, one, it is only effective against S. mansoni, which means it was primarily used in Brazil as a treatment against schistosomiasis because that is where S. mansoni is prevalent. But we also saw that schistosomes started to build up a resistance against OXA. So again, it's not a question of if schistosomes will build up resistance to praziquantel, it's a question of when. And so that means that one day the schistosomes will no longer be killed or paralyzed by praziquantel, which means we will have no treatment for schistosomiasis, which means people will just remain infected with schistosomiasis and have the side effects that come with chronic schistosomiasis, which is not great, right? So that's where Stefan and I step in. So Stefan started this project by looking at 400 commercially available anti-malarial drugs. And so we do this, and I talked a little bit about this in the paper that we wrote, but essentially repurposing marketed drugs allows for a more rapid approach to treatment, which while also avoiding long duration of developing novel treatments and subsequent high costs, right? So if we reuse a drug that is already on the market, then we already know what side effects are going to occur, we already know that it's effective, we already know that it's safe, and we don't have to run all of these trial and errors with creating new drugs. Right, and then we also, repurposing drugs allow us to avoid high failure rates with a decrease in risk, right? So anti-malarials were chosen to be evaluated against schistosomiasis as the liver flukes in schistosomes have the same blood feeding characteristics as the flukes that cause malaria, which means that these two species share similar heme degradation mechanisms. So if anti-malarials can target this pathway, then they should be able to target the blood digesting flukes of Schistosoma species, right? And so from there, they identified quinoxalin compounds that showed anti-cancer, anti-protozoal, anti-mycobacterial activities. And then from there, they further identified 6 nitroquinoxalin analogs that had activity against malaria, giardiasis, amoebiasis, trichomoniasis, and other diseases. And then from there, they identified a nitroquinoxalin-based lead compound that had activity against all of the previous diseases and activity against gram-positive bacteria. However, they ran into a problem, which was essentially, we want an oral drug, right? And so that means we want a drug that is water-soluble or hydrophilic. And they found that the nitroquinoxalin-based lead compound that they had was too lipophilic, which meant that it dissolved too well in fats and oils, right? And so we can think about this problem of this compound being too lipophilic in terms of log P. So when we increase log P, not only does a compound become more lipophilic, but a variety of consequences occur. So for instance, we also increase the binding to the enzyme or receptor, which is good because we're increasing the drug's ability to bind to the body. But we decrease aqueous solubility, which again is a problem because we want it to dissolve as an oral drug, right? But we also, as organic chemists, have to show this very fine line where It has to be hydrophilic enough to dissolve and get to our stomach, but lipophilic enough to cross our stomach barrier, to be absorbed by our stomach, because our stomach absorbs very few substances, although small amounts of certain lipid-soluble compounds can be taken up, right? And so we also know the famous line, like dissolves like, right? We know that water is polar, so if I have a compound that is also more polar, then it'll dissolve in water, right? We also increase the absorption through the cell membrane, which is beneficial, and we increase the binding to the blood plasma. So I like to think about the binding to the blood and tissue proteins in terms of like an example of ibuprofen. So a really interesting fact about ibuprofen is that 98% of it binds to blood plasma, which means that 2% of it is effective. So if we can somehow decrease the percentage of ibuprofen or a drug that binds to the blood plasma, then we can increase its effectiveness without increasing the dosage of the drug that we're taking, and hypothetically not increase the negative side effects or drug interactions that would occur, right? We also increase the binding to the heart ion channel, which is a really specific binding to the heart, and it'll result in a lot of negative side effects. So bottom line, if we lower log P, if we lower how lipophilic our compound is, then we can improve some of these consequences and ensure our compounds are more water soluble. So my basis for my research is, how do I make this lead compound more water soluble, more polar? So we first started in fall of 2020. And so Joe Heyman and I first started on this project by reducing this nitroquinoxaline lead compound. And as you can see, we're trying to take that NO2 and turn it into an NH2. So we first made a catalyst by adding zinc dust, nickel dichloride hexahydrate, water, and letting that solution mix overnight. We then heated it. We then added 20% acetic acid and heated it to 45 degrees Celsius. We then poured off the absolute alcohol, which is what the catalyst was stored in, added ethanol to the catalyst, and then added the catalyst to our lead compound and stirred it in a balloon apparatus at 35 degrees, and then recrystallized the resulting amine. This was the first reaction that I ran as a research student. So did it work? No, which means that we had to run another reduction. And so again, this is the same kind of goal of turning the NO2 into NH2, except this time we used a couple of different reagents and a different catalyst. So we added the lead compound and anhydrous ammonium formate, 10% palladium on carbon, and dry methanol. So 10% palladium on carbon was our catalyst for this reaction. We didn't make it. It was commercially available. And so we were hoping that potentially that could help out with our reduction failing. We then let the mixture stir for 35 minutes at room temperature, removed the catalyst by vacuum filtration, and then ran a hot filtration, and we stored the resulting amine in the fridge. Did this work? No. The hot filtration was not part of the literature procedure, but it was how we were going to try to get our product out of our solution. It took so much solvent and so much time. So then we kind of switched gears and we ran another reduction, except this time with a different compound, but still trying to take NO2 and turn it into NH2. So we first made the solution by adding the lead compound, 10% palladium on carbon, anhydrous ammonium, and dry methanol together. So this was a very similar procedure to reduction 2, except for the fact that we have a different starting compound, right? And so we then let the solution sit at room temperature for a week, in which the solution turned from this like gorgeous pink color to a dark brown liquid. You might be wondering why we let it sit for a week, because that's how long it took from us to do research 1 week to another, because we were like scheduled on Tuesdays and we were like, we'll just leave it and it'll be fine. And was that a good decision? TBD. We then rotovaped the dark brown liquid to obtain an oil. And then from there, we took the oil and added it to oxalic acid and microwaved that solution until it almost boiled over twice. And we obtained the golden yellow solution. We once again switched gears a little bit, and we ran a diazotization reaction. And so that type of reaction is essentially turning NH2 into a salt. So we can see here that we're now no longer trying to turn NH2 into NO2, but NH2 into that nitrogen triple bonded to the other nitrogen. So we did that by first making a 62% weight-by-weight sodium tetrafluoroborate solution, then mixing sodium nitrate and water together, and then mixing our lead compound, the sodium tetrafluoroborate solution and sodium nitrate solution together for 20 minutes between 0 degrees Celsius and 10 degrees Celsius, and then letting it sit for 24 hours and obtaining a final product. And this is where we were going to carry the diazotization products through to another reaction, but this is where fall term of 2020 ended. And I think Joe carried on this project, but I told Stefan, I was like, this is so frustrating. I don't know what is happening. I don't know what I'm doing. Can I just switch tracks? And so then for the spring, winter and spring of 2021, M. Harper and I worked on amine substituents. So we have this compound that we lovingly named Ron, after Ron Swanson, because Stefan called him a chunky boy. And so for quite a while, I took Ron, and I tried to add various amine substituents to him. So I tried to add ethyl N-diamine, and N-dimethyl ethyl N-diamine, and piperazine hexahydrate. So we did these three amine substituents because they were readily accessible for us, and there was already a literature precedent in how to add amine substituents like these to a compound like Ron. And so I did that by essentially taking 0.2 millimoles of Ron, 2 millimoles of the desired amine substituent, and roughly a milliliter of dimethylformamide together, letting the mixture stir for 48 hours at room temperature in 1 atmosphere, and then completing an aqueous workup of the product and purify the product using column chromatography, and then obviously characterize it using NMR. So this procedure is pretty simple, right? I'm just slapping my things together and waiting and hoping for the best. And so we wanted to see if there were any other things that I could add to Ron. And so we wanted to run a Sonogashira reaction and attach TMS acetylene to Ron using a Sonogashira reaction. So what does that look like? So essentially, we take an R group, which is a combination of carbons and hydrogens attached to a halide, which in this case, our big part of Ron is the R group with our chlorine as a halide. And then we react it to a compound looking like this, which in our case was TMS acetylene. And then we mix it with palladium catalyst, copper catalyst, and base, which in our case was palladium 2 acetate, copper iodide, and triphenylphosphine. And we should get a product that looks like this with TMS acetylene attached to Ron. So was this successful? No. Instead of making this, I made that. And I remember going to Stefan with his NMR and being like, I have no idea what is wrong. But as we can see, we should have, right, that very distinct NMR peak with the triple bonded carbon, right? I should have seen that. And I was like, Stefan, I don't know what's wrong. We both know Sonogashira is a pretty fundamental organic reaction. It should have worked. I have no idea what happened. And then after 30 minutes of us being we're not sure what happened, he was like, oh, I know what happened. You made an indole. I was like, what? And he was like, you made an indole. So you didn't discover this mechanism, but it is kind of cool because you made a ring. And I was like, okay. And so then I kind of went to the literature and I was like, how in the world did I make this indole? And so this indole is formed because we take a compound that looks like this, which Ron does look like that. We react it with these reagents, which in our case is TMS acetylene, palladium 2 catalyst, and triphenylphosphine, and we form an indole. So it's like not great that I did not make the product that I set out to make, but it was a really interesting part of my research because I accidentally made a ring and also found out that sometimes things don't go as you planned them to go. And honestly, it was just a really interesting part of my research to be like, accidentally made that. We do think that we made the molecule that we set out to make of TMS acetylene attached to RON at one point as an intermediate in that reaction, but there was no way of us knowing at what point during the reaction we had made that. And so I, again, went to Stefan and I was like, I don't know what I'm doing. Like, is there another part of this project that I could work on? Like, I really love doing this, but things are not going as planned. And so we essentially took Ron, the problem child, and I started to work on his precursor. And so this is 2,3-dichloroquinoxylin, and we can see that I am eliminating that NH, which should hopefully eliminate any problems of that NH acting as a nucleophile and creating an indole. And so what I did is I first tried to react 2,3-dichloroquinoxylin and propargylamine together, which is an amine substituent that I did try to attach to RON at one point. And so I tried to make something that looked like this, and I did that by first taking 2,3-dichloroquinoxylin, propargylamine, and potassium carbonate together at room temperature for 18 hours and letting it stir, and then extracting the product with an aqueous workup and purify through column chromatography, and then I took an NMR. And so this is an NMR of 2,3-dichloroquinoxylin and propargylamine together. And so we can see that those two hydrogens on the left benzene match to that green arrow. Those two hydrogens match the blue arrow. We can see the distinct broad NH peak between that 5 and 6 on my spectra. And then we can see the distinct CH way on the right side of my spectrum. And so at this point, I had worked a lot on this project and made a lot of molecules, trying to attach various amine substituents to RON and RON's precursor. And although we decided that, yes, I did make this compound, it wasn't pure. I ran so many columns. And we were like, okay, what else could we do? Because we were, as I said, having problems with purity. Also, we were having problems with what is called yield. I remember one time on this research project, I did my math and I got like a 0.37% yield, and it was like a very sad day for Ezra because I was like, that's not even 1%, what? And then someone was like, it's okay, it's gonna be fine, we'll do it again, or like we'll find another reaction. And I was like, great, I'm gonna go lay down, face down on the ground for just a few moments, and then I'll be back, but I just need to wallow in this sadness for just a little bit, and then I'll be good. So after wallowing in my sadness for a little bit, we came up with a plan. So instead of, because for quite a while, what we were doing is we were taking our nitroquinoxylin-based lead compound and trying to add various amine substituents to that, right? And so Stefan had the idea of, what if we did that, but in reverse order? So instead of adding amine substituents to our lead compound, what if we synthesized something, attached an amine substituent to that, and then added it to our lead compound? And so at the very end of this research project, I did that. And so I first started with an Azid synthesis. And so what that means is I essentially took this NH2 and turned it into an N3. And so I did that by first making a 50% sulfuric acid solution, adding aniline, that sulfuric acid solution together, and sodium nitrate together, and mixed that for an hour. And then I added sodium azid in water dropwise to solution from step 2. And so then, unfortunately, that is where my part of this research project ends, because life gets hectic and I am like a busy individual, unfortunately. But that doesn't mean that this is where the project ends. There's actually quite a bit of work that can be done. And so future work continuing the Azid synthesis would be to actually confirm that I did make the Azid through NMR. And this would definitely just be a little tricky of a step, because to ensure that I made it, you would have to take an NMR, which means we'd have to get rid of the solvent that it is in, which means you'd have to rotovap it, which means you would have to add, you would pressurize and heat it. Which you're not supposed to do, because azids are super reactive. And I think I did rotovap this at one point in time, and I was like, this is the most terrifying thing I've ever done, because I don't know if this is gonna explode or not. It didn't, but it was very funny to me to be like, oh, I'm not supposed to do any of this. I'm not supposed to add heat or pressure to this compound, but I'm literally doing that because I literally need to do it. So first confirm that I actually made that, and then react the azid with propargylamine to make that chonky boy, and then attach it to 2,3-dichloroquinoxylin. So this strategy is advantageous because we don't necessarily need to use propargylamine as our amine substituent. We can actually run multiple parallel reactions with a variety of amine substituents. And then also we could try to attach these to RON. We don't need to use 2,3-dichloroquinoxylin. So this strategy, as long as we confirm that we did make the azid and it is pure enough to carry through to another reaction, we can run a lot of reactions using this strategy. Now, more general future work would include characterizing and purifying compounds synthesized in both pathways of the synthesis of reduction and substitution. So I only had one NMR spectra in my presentation, but I probably made upwards of 20 compounds that are all sitting in a little tub in the fridge, just waiting to be purified and characterized through NMR. And then our end goal would be to send these purified compounds off to be tested against rats infected with schistosomiasis and see how effective they are as a treatment and if there are any issues with toxicity. Thank you so much for listening. Does anyone have any questions?
Okay, we're going to try unmuting the pod mics for questions, so please don't talk to your neighbor if somebody's asking a question. You may raise your hand if you'd like to ask a question. Zoom people, we will get to you in a moment.
Yeah, I don't know how to do that. I'm sorry.
In-person people, does anybody have a question? Jesse.
So on slide 24, you mentioned that you had a low yield and a lot of side products that you were getting, undesired side products. Were you able to characterize or identify any of those side products?
No. Honestly, throughout this entire research project, Stefan and I's goal was just like turn out compounds, like just get as many compounds, get as many procedures done, and then we can deal with like characterization and purification later, because again, as I said, the like end goal is to like just take a ton of compounds and send them all at once. So no, unfortunately, I was not able to do that.
Just while I've got this up, this is actually pretty clean.
Oh,
the only
rip.
2 things that we see here are the product that they want and the starting material.
Yeah,
So the really big piece to the left are your starting material.
right.
Everything else is the weight.
Again, this was like, I don't know when this was, but I don't have the greatest memory. So yeah. Also, early Ezra did not really know how to like do a lab notebook. So like my notes, not good. Not great. Yes.
So the question on, or you tried to do a trimethylsilane addition.
Yeah.
Why? Just curious.
That's
Would
a
that
great
be a goal?
question. I think it's because we wanted to potentially carry through Ron with TMS acetylene to try to add something else, right?
Yeah, so what?
But
what
then
would
that
be the
didn't work.
difference between using TMS acetylene and just using acetylene?
Right.
Why
Because
is
of
it
this,
easier to use TMS acetylene than straight up acetylene?
because of this, the carbon, right?
Yeah, what do you know about acetylene?
Well, it looks weird.
Yeah, it's a gas, right?
Yeah.
Yeah.
Yeah, so it was easier for us to start with the TMS acetylene and then hopefully carry through that product to add other substituents to it. But then Ron was like, nah, I'm not going to do that. I don't want that to happen. And we were like, okay.
Yeah, I have, I guess, 2 questions.
Okay.
The first one, you mentioned that you used a microwave. What kind of microwave did you use?
We used a kitchen microwave, not the one in the break room, but just a kitchen microwave. I couldn't even tell you the make and model. It was literally a kitchen microwave.
And the second one actually does relate to this because you talked about, this was when you made the indole, right?
Yeah.
It was during this reaction. Do you think there'd be a way to control for the intermediate that you initially wanted? Because you said it might have been formed throughout the reaction.
Right. I think, like, could we have monitored the reaction by using TLC and ensuring, like, when did we make the actual product? Yes. Did we decide that was a good use of time and resources? No. Because we knew that we had 2,3-dichlorochloronoxylin. We knew that it was available. We knew if we got rid of, or at least we hoped if we got rid of the NH, that would get rid of the problem of creating an indole. And so we kind of were just like, Ron's a problem child, let's move on. But yeah, I do think that we could have spent time in trying to determine at what point did we make the product that we actually wanted.
Yes.
So I was like able to follow pretty well with the chemistry, but I'm gonna ask more of like a biologically related question.
Yikes.
That's what I'm comfortable with. Do you know why the drugs that you showed us are effective at being antiparasitic? Like what's the
Yeah, so this is actually really interesting and a part of the writing that Stefan and I did. We actually don't know what makes praziquantel an effective drug against schistosomiasis. It's like actually kind of a hotly debated topic. It was really interesting reading all of these theories because papers would be like, this person said that, but that's wrong. But we actually don't know. Like some people believe that it's effective because it paralyzes the hooks that schistosomes have that can let them attach themselves into our bodies. And so if those hooks are paralyzed, they no longer attach into our bodies and then are just excreted back out. Some people believe that praziquantel prevents schistosomes from uptaking nutrients, and so then they obviously die because of a lack of nutrition. But we actually don't know what makes praziquantel an effective drug against schistosomiasis, which is why drug development for schistosomiasis is kind of a guessing game because we don't know what about this compound makes it effective, which means we kind of just guess. Yeah.
follow-up question?
Yes.
Do only the adults have those hooks, and that's why it's only effective against
Maybe. I honestly do not know. But well, because maybe, not sure. TBD. Could not tell you.
Does anybody on Zoom want to ask a question? I didn't
don't-
see any questions in the chat. This is your moment if you want to unmute, Zoom people. Everyone in the chat is happy, can confirm.
Oh.
All right, in-person people, does anyone else have lingering questions for Ezra? All right, well, let's thank our speaker again.
Should I do anything?
All right, friends, Glorielli's talk is up next in a few, so have a cookie, talk to your neighbor. We will get the technology switched, and then we will begin at 4 o'clock.
I didn't bring a lot. So, when I was working on this